Hi, so today I'm going to talk to you about adapting methods for new challenges in describing and interpreting the past, present, and future of anthropogenic sediments. So, what we're going to sort of be addressing today is having a look at specifically the methods and how we go about, seeing how far different methods can reach before they stop working, and then how we can start figuring out ways in which we can now address those new gaps. So, how I got into methods, well, I started as a geologist, as a traditional geologist, back in 2009 when I started my undergraduate degree. And through there, I was learning a lot of traditional geological methods, and I ended up in sedimentology. And then for my PhD, I was working on fluvial meandering systems. And I ended up creating these methods for how we can try to assess the different shapes of methods in a quantifiable shapes of meanders, sorry, in a quantifiable way. And what I think I learned from that was that the goal with creating any method must be to invent as little as possible. And this is just so important when it comes to usability of these methods and trying to communicate these findings, having impact with the method so that it's easy to distribute, take on board, and also like make it easy for people to use and adapt the skills that they already have. Um, so then I kind of like went from there into teaching sedimentology, and it was when I went to Louisiana in 2019 that there was the next shift for me in methods because I went to a really multidisciplinary event which got me thinking differently about geology being the only path for understanding the world, because there are many different disciplines that sit at this interface of human-earth interactions, and the diversity of practice amongst all of that really helped me to start to understand a bit better how we can begin to understand the diversity of Earth through these different practices. So, for example, if you're standing next to a river and you've got a levee along the Mississippi River, that levee has not formed due to processes that we would recognize from, typical fluvial processes, as it were. So they haven't evolved through flood events directly, but it's because of flood events that has then led to policies and also engineering that then is to create these levees out of concrete rather than sand. And they're kept shored up, and the river itself now sits quite high in the landscape because of the extent of these levees. There's also a really important economic driver behind that. And all of this really like hammered home to me how no discipline is alone. And it helped me to start thinking about the different lenses through which we can see the environment. Um, and that kind of multidisciplinary thinking to me is like spokes on a wheel, right? We're just geology and geomorphology is just one spoke on this wheel. And so when I then came home from this event, I went back to my methods on geology and found that we really didn't have enough stuff that could really link the physical and social components together in a way that really felt like it was answering what I really thought that I needed to figure out the next steps of this pathway. So about a year later, I founded the Anthropocene Sediment Network in 2020, and yeah, we'll see more about the ASN as we go through, but I just kind of through exploring this and through meeting people through this network, it's really made me realize how much of the world that we have changed and how changed the world is now because of us. So I'm just going to show you a few of the key things that are on my mind a lot of the time when we're thinking about how much we've changed the world in terms of sediments. So this is a study from 2022 by Joe Svitsky, and they basically found that we've massively increased the amount of material that's moved on Earth and that we move more material on Earth than natural systems by quite some margin. So in 1950, we were moving 70.2 gigatons per year of sediment, and by 2010, we were moving nearly 300 gigatons. And if you want to compare that to natural systems, in 2010, alien transport was moving 1.5 gigatons, and fluvial transport was 11.3. And yeah, you can add all those numbers up and come nowhere close to the amount that we were moving around in 2010. So this is so important. Like we are now the predominant drivers of the processes and flux of loads in these in how sediment is being directed around the landscape. And then when we're trying to describe the sediment, a lot of it is very polluted, a lot of it has got large amounts of plastic in it. And so if we're looking at these images here of like what's actually going on underneath the ocean, we can find these, recognizable objects. That is a bucket over there, for example, and things. But beyond that, how do we describe what's actually going on in terms of the sedimentology? It's a big issue. And then also massive amounts of land use change. We've shifted geomorphologies and landscapes and land dynamics around the world. And then just thinking about sediment behind dams, the ones in green are the only rivers in the world that have been assessed as essentially non-impacted by river dams. Everything else is heavily or moderately impacted. Sediment is literally directly removed from these river systems, which means that the signals are shredding and changing downstream. So this is sand mining, and then the resulting river has got a different water depth and different velocity. And then we've got all the new stuff that we're adding in. So plastics, and we've got a lot of plastics that's all being added with 400 billion in planned investments to make petroleum-based plastics, continuing into the future. And all of this material is forming deposits. So if we're trying to invent as little as possible, if this is a deposit, then this material is sediment. So let's just use this as a thought experiment and consider everything to be sediment. So in 2020, the collective mass of human-made materials surpassed that of Earth's total biomass. So that suggests that a significant portion of the sedimentological record being formed today could comprise of anthropogenic materials. Now let's just hold that for a minute. In 2020, 50% of the material, if it was a surpassing, 50% of the material was natural and 50% was made by us. That means that future geologists are going to look back on the year 2020 and half of the fossils that they found, we have made. Half of them. That's astonishing. And we really need, therefore, to begin describing all of this stuff in a way that is consistent and is geological. So we need to do some of this stuff. And so let's just consider it sediment just for the philosophy and the debate. Traditional sedimentology doesn't fully account for these human-made sediments yet, and environmental assessments lack methods to integrate anthropogenic materials into analyses in the level of detail that sedimentologists need. So without a sedimentological approach to consider these materials, we're not really able to fully consider their risks, impact on the present environment, long-term legacies, and much, much more, how they're interacting with the processes that are currently going on and things as well. So as a discipline, we've got to establish a few things. And in this presentation, we're going to talk about how plastics are impacting sedimentary processes, how we're assessing physical properties of anthropogenic materials, and also how we can adapt the field methods that we already use and geological skills into a contemporary context. And then last but not least, how we can meaningfully engage on this with other disciplines. So for plastics and sediments, I published this a couple of years ago, and what it effectively showed us is that we need loads of further studies. It got picked up by a bunch of different magazines and online articles, which all showed that there was a lot of interest in all of this, and the concept of the unknown unknown of what is plastic doing in the world is far from over. We've got an awful lot of discovery to do in this yet. So this is a classic riverbed, dune, and so we're just going to, well, it's a ripple really, but if you watch this bit here, we've got, that was a cigarette filter that eroded out, and it's left us with this pit. And when we have these individual erosions, these pits can form. And the reasons that plastic behaves a bit differently within these systems is threefold. The first thing is that the erosion threshold is much lower. The second reason is that the roughness of the particles is lower, which means that there's less friction of the particles on the surface, and so um, it can become exposed more rapidly, and then if it's exposed, then the lower erosion threshold can lead to its removal more quickly. And also the scale of them because of the difference in density. So the scale of them leads to different properties as well. So just watch that, it's off. Um, so yeah, the different scale leads to some erosion and scouring around the particle, and that erosion and scouring then can change how things happen. Now, after those two particles got removed, what you'll notice is that the bed form, which used to match the shapes along the top, is now flattened, and that collapse is shifting the way in which this bed form is moving, migrating, altering. And even though this just seems like a small thing, if you imagine this happening time and time again along a river system, then the lower the lower bed forms and the flatter bed forms or the collapsed bed forms and this kind of like cycle of building and then collapsing of these systems will lead to a difference in the flux of how the material is transporting downstream. We don't know all the answers to it yet because there've only been a handful of studies. But yeah, it's really there's a lot to study there. So importantly, plastic is not passive on riverbeds. Even though it's easier to find the stuff that's floating on the surface, it's really important to look at what's underneath as well. Plastic inclusion changes the ratio of suspended load to bed load material, and the inclusion of plastic encourages rivers to develop more conduit-like properties and create heterogeneous deposits. So we found a new subdiscipline of sedimentology, which is plastic and sediment interactions, which in itself brings to the forefront some really interesting methodological questions. But the problem is that within this, then if I'm thinking about plastic as a sediment, how on earth do I classify it? Because it's nothing like a siliciclastic component. It's got a hole in it. It's going to be more stable for longer. It's not going to break down as rapidly. It's going to have a completely different set of kind of parameters in the environment. So what it made me realize is that we need to reach a point where we're understanding where plastic and other pollutants can be fully considered and integrated into models as a sedimentary component, which means assessing things as if they are plastic, as if they are sediment. So why sedimentology is so ideal for all of this is that it puts this objective analysis before interpretation. So if you call something a bottle, then it's an interpretation technically of its prior use. And as materials degrade more and more, then the miscellaneous category is only going to grow. And there are some people who can identify where something is from the tiniest fragment, but the skill set for that is incredibly huge. And so what we need to do is try and create a way that we can be more descriptive first, and then interpretation can come later. So as things break down more and more in the environment, we will logarithmically get loads more microplastics. These things, it's double and double and double, isn't it, when things are breaking down? So exponentially, that's the word I was looking for, exponentially get more microplastics. So this miscellaneous category is only going to grow, so we need to be describing how these materials look to us, and then from there we can start doing more work. There's also a deeply rooted allowance for temporality. So sedimentology can be used to understand deep time, deep future, and temporal transformation of particles and environments, which is really important. Systematic, consistent, and flexible framework. So there's this logical and objective way to extend on and build on what is a very foundational and important backbone. You could show anybody in the world a sedimentary log and they will understand it. Sedimentologists, that is, and they'll understand it and be able to do some complementary work or further analysis on that work through understanding this backbone. So it's really a very valuable, very logical, and I think central way that we can really understand some of these materials. When we're thinking about anthropogenic clasts, We need to be not just classifying, but ideally quantifying these anthropogenic materials because they can be any combination of properties, which makes them really, really hard. It's anything you can imagine. It's more complex than just adding plastics into sedimentological models because of the difference in properties of plastic materials and how they're like transforming sedimentologically en route. Existing schemes work really well for the projects that they were designed for. But if we're going to unify them and think about all of the sedimentologically, we need to meaningfully consider anthropogenic materials as sediment. Now, there are loads of groups of people who look at collections of anthropogenic material, um, and they're all under a necessary specialized focus. And so, what I'm saying here isn't that we have to, you know, not do anything else except for these methods that I'm proposing. I'm saying that if we want to consider everything as sediment and we're following this experiment, then we can follow this method. But I'm just explaining why this doesn't exist just now. So archaeologists will consider anthropogenic materials as artifacts, but the sediment surrounding the artifacts is not always studied. Soil scientists will consider anthropogenic items as clasts, but often there is a plastic inclusive framework, but only plastics delineated by that. Engineering geologists use some very generalistic terms that are designed to understand the structure of the ground, but these are too generalistic to understand origins and future of the deposit, and in particular process for us. And then environmental sampling is undertaken on many materials to focus on quantifying mass, form, and composition. But we cannot form a unified sedimentological perspective from what exists, so we do need an integrated classification scheme that can capture the full spectrum of anthropogenic impacts on sedimentary environments. And the potential of sedimentology to further enhance this understanding of material is very substantial, and it relies on the development of a robust classification framework. So these two classification schemes I'm going to show you. I'm going to show you how I built them for the first time, and the classification schemes for anthropogenic material needs to mirror the adaptability and framework of traditional sedimentology, so we're inventing as little as possible. It's appropriately designed to provide a robust foundation for descriptors and nomenclature, which means that the most appropriate facies scheme can be developed to meet the specific objectives of a study. And the framework will specifically focus on the description of field-scale sedimentological descriptors. But importantly, because we're inventing as little as possible and we're directly adapting methods and methodological principles from traditional sciences, it can be used inexpensively with skills we already have in any environment. That to me was the most important thing about drawing all this together. So, whilst size itself is objective, the widely accepted nomenclature is very variable, which makes it really interpretive. So, 5 millimeters could be, sorry, spilling my drink everywhere, sorry. Um, so 5 millimeters could be microplastic, mesoplastic, or macroplastic, depending on which study you look at. And that's really confusing because what that means is that there's no consistency in what that word means. So if you're looking at nomenclature, then really those words have ended up meaning nothing. And yes, we could reduce that down to just using sizes, but then that would be the equivalent of every single time we describe something, never using the words sand or silt or clay or like that's just weird, right? So we need to have some sort of nomenclature for understanding and communicating what we mean by each of these subgroups and generally speaking, what's the size range that we're looking into. So what we did was basically separate this based on usage. Um, micrometer, nanoplastic was in nanoscale, and then microplastic begins at 1 micrometer and then comes up to 5 millimeters, which is pretty well embedded with classifications by marine ocean scientists who, some of it's to do with what harms fish when it's ingested, some of it's to do with net size, the size of nets and things, so mesh on nets. So 5 millimeters just is at this point. So that's microplastic. And then there's mesoplastic, which some people don't use, but I think it's a really useful subcategory because to me it's the size of things that will fit in your pocket. So it's things that you might typically kind of have in your pocket, things that can fit down drains in streets, very easily. So we're thinking of things like hair ties, sweet wrappers, tissues, things like that that are like under 5 centimeters when everything's screwed up. Um, then 5 centimeters to 1 meter is stuff that might be more typically distributed in a household. Most household waste bins are about a meter in size, and that is a Western-centric perspective. But all over the world, these materials are sort of distributed, and because of the scale of a human, of us, that means that things that we tend to deal with tend to be less than a meter size. Otherwise, it's a bit cumbersome because of how big we are relative to a meter in general. I'm being very generalistic. This has to be generalistic. And then we've got 1 meter to 10 meters. And I thought that 10 meters was a really interesting sort of cut-off point because there are things that are over 10 meters long, and they tend to be these very specialist things such as windmill turbines or elements of cruise ships or bridges and things that can become sedimentary components if they're kind of like, mismanaged or in a refuse site or something. And when you start thinking about where those really big things come from, these major, things like, I don't know, train carriages or plane wings. You see loads of things like this in specialist facilities where there is a lot of one item where things go to be broken down. And so I think having this gigaplastic category really encourages us to think about this distribution of these materials. Household materials under a meter tend to go to landfill sites, but then what happens when they get bigger? And it actually gets very interestingly more and more specialist as we're starting to sort of, if it's managed waste. So I thought that was quite important to add. And gigaplastic, the term was new to this study. Then there's shape. So if we're looking at shape, this was the most complicated one. But if we're looking at shape for uh, sedimentology, we tend to go around these two methods. Now, this is the Zing classification, where we're looking at elongation versus flatness of a shape. And there are more complex versions of this, but this one works, and it works because it's simple. And this is why it's really important to think about the methods and the application of methods when we're developing things, because yes, you can come up with a complex method, as I found out through my PhD, but if it's not intuitive, if it's not usable in an easy kind of way, it's very, very difficult to adopt. Um, so Zing hit the nail on the head with like getting this just to the right level of usability and adoption. And so if we use this for anthropogenic materials, you just sort of draw a locus around the overall shape, take your average measurements, and then you can plot things quantitatively onto this, which is awesome. But then this causes problems. So we're looking over on the other side of this slide. We've got these sphericities and angularities. This is really useful for things like microplastics, because of course we can talk about very angular particles, which is how I prefer to describe them rather than fragments, because a fragment is technically everything, and technically if something is angular, it doesn't necessarily mean it's a fragment, but that's a whole thing. And if you're interested in that, it is written up in full in this paper. Um, I think section 4 or something, so you can go and read the full fragment rant there if you're interested. Um, but basically, the issue is, right, if we're looking at, say, paper or, sweet wrappers or a hairbrush, how on earth do you classify that within here? Well, it gets impossible, right? So the problem with a piece of paper is that texturally it's smooth, but it's got angular corners, right? So it's very angular, but with that texture, which means it just doesn't work. And then we've got somewhere in the middle with these sweet wrappers, which are sort of crinkled, but they are very angular because they've got these sort of very angular components to them, but their overall shape is sort of sub-rounded. So how do you deal with that? And then what on earth do you do with a hairbrush? It gets really hard. And this is what we came up with. So we did roundness and removed the texture from them. So this is just for morphology now, and added a corner to each. So you're not just dealing with grain, you can deal with any component of it as well. And then added texture as density, but then also intensity, which is really important when you're starting to think about the surface area that's exposed to the environment for microplastic creation. So for paper, you'd then have this as angular, 90 degrees. So that would be angular, and it would be low density texture, depending on the type of paper. Maybe you have low density texture with like very low intensity or no intensity as well. And then with these, sweet wrappers, you'd have quite an intense texture, and then you'd be looking at maybe angular, very angular. For the rest of it. And then for the hairbrush, because we've got these like, bristles and things, you could look at maybe there's a section that is very high intensity texture, or you could describe it as a series of rods, depending on what scale the texture was made of a series of rods, depending on what scale that you wanted to do your assessment analysis of. So this gives us a full set of tools where we can start describing things sedimentologically. Now, the next problem with shape is holes. Okay, so how many holes does a straw have? Now, so does it have two holes, one at the top and one at the bottom, or one really long hole, or zero holes? But if you puncture a side in the hole, it would have one hole because an undamaged straw starts with zero holes. So this last one, I think we can immediately dismiss because if it's got zero holes, then we're assuming that there has to be an intended that basically you're interpreting the word whole to mean added, right? And that's not necessarily what whole means. But the argument generally tends to be between two and one holes. Now, there is an answer to this, and there's a correct answer to this. The answer is one hole. The hole is really long. And bear with me, because I know that this can be contentious, but bear with me. So I actually came up with this next part of the classification scheme whilst in a YouTube rabbit hole at 2 o'clock in the morning in the middle of the pandemic. So this is what I mean. I haven't told some of these stories before. But there's this video by Vsauce called "How Many Holes Does a Human Have?" And he goes through discussing, pores and ears, as you can see, he's describing there. And then interestingly, it ends up being about sinuses, and most of our holes are in our head. So what humans actually are 7-hole donuts, depending on what your sinus structure is. But watch the video; it's genuinely fascinating. But anyway, so humans are 7-hole donuts, and the reason that you can come to this understanding is because of a branch of mathematics called topology, and this is called homeomorphic topological homeomorphism. So topological in surfaces and shapes, and then homeomorphism, which is morphing and it sort of having like this homogeneous nature to it. So morphing between these homogeneous states. And it basically posits that you can take a mug and turn it into a donut. And there is a famous topological joke saying, why did the topologist eat his mug? Because he thought it was a donut, which is apparently hilarious to mathematicians. But what it means is that without breaking the surface of a shape, you can remove a blind hole. So a blind hole would be the place where you put your coffee in the mug. You can remove a blind hole, but you cannot remove a through hole without breaking the surface of the shape. And so that gives us an amazing quantifiable method by which we can actually start to understand a through hole. And from that, I then developed the rest of it. So if a through hole has to be without breaking the shape, then a blind hole just needed some quantification. So I came up with some like constraints over what do I mean by blind hole. And then I added closed hole, which technically doesn't quite topologically work within the maths, but it's really important for buoyancy of these systems. And then from this came the notation of TBC, and this notation then allows us to start assessing what kinds of holes that we have within a shape or system. So this one's a bit more complex than the straw, and you can see we've got 2 through holes, which then means that we have a double torus. The donut's also called a torus. If we have a plastic shopping bag, we have one blind hole and two through holes. So that would also end up being this shape if you flattened the whole thing out. And it's really important then if we're looking at things like bottles, because with the lid on or lid off, we end up with different hole types, which then affects its motion through the environment. So that's another part of this classification scheme. And then last but not least, absolute density is really important. Obviously, polymer type is important, but when you add other components to it, such as organics, air, and sand, these priorities change. Polymer types are also not pure, which means that they are variable. So when we're sort of thinking about, how things are behaving in the environment, whether it's positively, neutrally, or negatively buoyant, is incredibly important when we're really coming to understand some of these mobility challenges of how things move in the environment. These ones at the top have their lids on. These ones down here have their lids off, and therefore they're more prone to changing states, which is another thing of the process that these bottles will go on through the environment. So the next thing to do then is to think about what happens when we take all these individual items and create layers with them, or create anthropogenic facies, as we're going to call it. So this is a Mardi Gras deposit, as it were. This is what happens after the Mardi Gras parades in New Orleans, in Louisiana. It's sort of a sedimentary layer. Yeah, these are the Mardi Gras beads. They actually have a huge proponent of lead in them. That's a whole other talk. So then when we're going through these different compositions and descriptions, the first step is to describe the anthropogenic materials, which we've just done. Then we describe the sediment surrounding the anthropogenic material, which we can do using standard methods. And then anything that's within the anthropogenic material. So if we have a bottle that's full of sand, we need to describe the sand that's in the bottle because it might be different from where that bottle has ended up. So we need to sort of like have a look at the chemistry of that too. And then all of this stuff is just typical geological framing, class supported, stratiforming, surface modifying, unconsolidated, non-compacted. So again, inventing as little as possible, trying to transform this thinking into something that we can use in field work. Then I did some sedimentary structures, used bound and unbound and baffled from the Dunham classification scheme for looking at carbonate rocks. And then started to think about what's going to be important for how we understand and interpret process from what we're looking at within these deposits. So if it is, say, for example, in a net, this is tangled, which would be bound before and during deposition, potentially. If it's baffled, such as a shopping cart in a river, it could be captured and bound during deposition as well. So how are we like creating these components, right? And then a lot of this material is just examples. You can also maybe throw some glitter into some flame structures and make some, make some new things in there as well. And anywhere that microplastics go, it technically exists. So this is anything that you can imagine. It's somewhere within these components, right? So we're thinking about the methods of organization, where it was integrated within the process, how it might be organized due to the nature of these mechanisms, and then whether we're looking at something that has been unbound or bedded or uncontained. So there's a huge amount to discuss in this as well. This second paper is just supposed to be the beginning of the conversation. So thinking about sedimentary facies and things is, there's a lot more to do. And then last but not least, we're looking at the nomenclature of all of this. So this is how we can create names of materials that might be around us, right? So if something is a mixture of plastic and sand, where you've got these proportions between the sediment and the anthropogenic material, then that could be siliciplastic, with silica representing the sand and then plastic representing the plastic. And this is following on from methods that people are already using, like plastiglomerate, for example. So this is to do with the different proportions, though, of how this is. So I've just framed this in a way that allows us to extend logically using sedimentological frameworks onto what we already have. And so we can end up with things that, and these nice combinations of prefixes and suffixes that can again be logically built on. So if we're applying this and then using descriptors, the bed scale, grain scale descriptors we saw right early on with those kind of cross sections. But we've got here combined anthropoid, massive organoplastic, baffled silicimetallic, massive organoplastic, layered anthropoid, and a unidirectional siliciplastic. And then we can describe all of these using things like stratiforming, strata-containing, surface modifying, subsurface modifying, cemented, unconsolidated, compacted, non-compacted, intermeshed, bulk density, and many more with the grain scale as well. Sorting, orientation are things that we are used to using within these sorts of studies. So this all comes together into these two kind of summary sheets or cheat sheets, which are available in supplementary material for both these papers. But basically, the issue that remains after all of this is that we still have a huge fundamental challenge in understanding the context and cause of change in these environments. So if we're going back to the beginning of the talk where I was discussing some of these broad scale alterations and changes, we're now at a point where we have a framework where as geomorphologists we can go into the environment and start describing stuff, but there's still this fundamental challenging concept of like understanding this cause of change, and it's impacting our ability to do inductive science because there are these social additions and social components to the formational mechanisms and processes behind things that is far beyond natural that we need to find a way to discuss. So within geology, we have uniformitarianism, which relies on process continuity, rate consistency, and uniformity of physical laws. So process continuity states that the same types of processes have always occurred and in the same manner. Rate consistency considers that processes have occurred at generally comparable rates over geological time, which is similar in principle to gradualism. And then uniformity of physical laws is essentially coincident with actualism, which dictates that the same physical laws apply across all of Earth's history. So that's stuff like gravity, right? So Charles Lyell says famously that the present is the key to the past and the past is the key to the future. Now, living in this present moment, it is very difficult to believe that. And there have been many shifts over geological time where that also has not necessarily happened. So if we're thinking about the introduction of land plants, the evolution, of land plants, where before land plants, rivers maybe behaved completely differently to afterwards because of rooting mechanisms and soil formations. So yes, to an extent, uniformitarianism is completely still useful, but we just need to talk about it a little bit. So the development of uniformitarianism has been it happened over a long, long time since like 1700s, really, with some of Comte de Buffon's original studies, and then it was formalized in the 1800s with William Whewell. But uniformitarianism has since been revisited and revised many times with the aim of clarifying its definition, which has arguably led to today's semantic chaos. Not my words, but I think it's a nice way of describing what's kind of ended up happening. It's essentially become a law of simplicity based on Charles Lyell's entire theoretical system. And substantive uniformitarianism, which is that the present is the key to the past, has been largely disproved and considered to be a bit misleading. But methodological uniformitarianism, through which we use present-day understanding to apply it to the past or the future, is really important for relating flume experiments to the natural world, and also through understanding physics and gravity and flow. And hypothesis generation, it's really, really important. So I'm not dismissing it at all. I'm not trying to replace anything, but I'm just sort of trying to highlight where some of these weaknesses might be and where some of the strengths are as well. So to talk about more broadly some of the limitations of uniformitarianism, the process continuity and rate consistency are not appropriate under all settings. It becomes really difficult to apply when we're looking at events, complex systems displaying nonlinearity, time lags, and feedback loops, and us as well, because we make decisions that shift stuff on such a global scale. So these challenges are amplified when considering human activities because a law of simplicity gets really difficult to uphold. And if something does not obey uniformitarianism, that is technically an exclusion and it is not an analytical framework. So we are somewhat consciously or subconsciously, I don't know what the balance is, but we're not necessarily assessing things through, you know, considering basically we don't have a way to think about, we don't have a space to think about something that isn't the same as the past in some ways. It's hard to explain, but I hope we get there in a sec. So human-altered landscapes include socio-political and economic drivers, so cause and effect relationships become decoupled from geohistoric baselines and entangled with human agency. So effectively, if we're thinking about cause and effect relationships, right? If we just go back to thinking about that levee by the river, right? The processes that have caused the levee are not river is flooding. And that if it's the river that's flooding, then that's uniformitarianism because that's the presence, the key to the past. Instead, it's layered with concrete, which is to do with all sorts of things to do with economics and also, these social pressures and politics and things. And that is why the levee ends up being built, and also for safety and community building and things, of course. But it's really, really, really important to understand that if we do not have the skill set or understanding as geomorphologists to understand the processes of development of geomorphological features, then we can't meaningfully understand the cause and effect relationships around those features. So we can't make testable hypotheses and can't do inductive science around it, which means that we've got to do multidisciplinary work and things. And this is all about the causal story. So we need to understand baselines and context, physical influences and constraints on material movement within the environment, how we are temporary hosts of objects in a material flow. This is one of my reasons for suggesting that everything is sediment, and really start digging into this complexity of the human-earth interface from pollution all the way to urbanization. And this is because the mechanism is mostly us, and it is our decisions, which are weird, and there is, hardly any precedent for anything like that in the geological record. So whilst there are elements of uniformitarianism that still exist, we need something else. Introducing discorditarianism. So this does not in any way delete uniformitarianism. This fits into part two. But the first part of discorditarianism is identifying what is being compared, what time horizon objects, exactly what are you comparing to what and why. Then part two is what elements of uniformitarianism is still going to apply, so process, rate, or physical laws. And then part three and part four is how we would spatially or temporally describe the discordance. Is it, frequent? Is it a one-off event? Is it changing through time? What's the longevity of the impact? And then the fifth one is, I find the most exciting, which is what are the overarching forces? So is it tourism? Is it a new law that's changed the way that the river needs to be managed? Is it a new plant species that's come in because of, someone's dumped the ballast of a ship from a ship over by the beach? There are a lot of social forces and a lot of physical forces, and this help gives us a little window into being able to describe all of them and to help us to understand the challenges and how we can maybe come about, what disciplines we might need to kind of maybe fill that gap. And so this helps us fill in this mechanism element in the cause-effect relationship within our causal story. So it provides a structured method to evaluate the extent and nature of Earth's deposits that reflect uniformity, so through simplicity, and discordance or complexity within Earth systems. Discorditarianism is crystallizing the conceptual space that presents an objective bridge between process-based Earth system science and evidence-based stratigraphy. And it's designed to complement uniformitarianism, not replacing anything. I like uniformitarianism too. We're not getting rid of it. And whilst it helps to expand the potential for science to incorporate human impact without oversimplistic collapsing it into a homogeneous force, it is importantly not human-centric. It can be applied to any change or difference, so it is really, really, really exciting for multidisciplinary work. And this brings us really neatly to the very last part of my talk, where I'm going to tell you about the Anthropocene Sediment Network. So By sediment, we're referring to anything that can move on Earth, from sand on a beach to the device that you are reading this on, because one day it will end up in a landfill site or at the bottom of the ocean, which is a sedimentary process. Just because we're involved in it does not mean it can't be sediment. And then by Anthropocene, we refer to now, we're not involved in any GSSP discussions, that belongs to other groups. So our network encourages collaboration and dialogue, promoting advances in research across disciplines to tackle these unique dynamics of how we're going to do this multidisciplinary work on our changing planet. We've got this really cool model for combining foundational concepts from sedimentology and loads of other disciplines to address these complex human-induced environmental changes. And we sit between physical and social disciplines in a really cool way. So just to summarize, we have changed and continue to change the geology of Earth, and sediments are by far the most affected in the geological system. All materials that move across Earth's processes, whether natural or human-made, undergo sedimentary processes, and we need methods to aid these understandings. So methodologies and classification frameworks help us to crystallize these understandings and communicate them as well within environmental dynamics and examine a more nuanced approach towards the significance of anthropogenic influence within the stratigraphic record of contemporary Earth. And this quaternionism aids with capturing this system complexity and, importantly, helping us do some really important multidisciplinary studies. So my final slide, this is a recording, so of course, any questions do please email me. I'm more than happy to hear from anyone. And if you're interested in this kind of thing, do feel free to join the Anthropocene Sediment Network. You just have to go to the website, click Get Involved, and you'll be signed up to our mailing list. And we have loads of cool things coming up in 2026 and even some things planned for 2027 already. So yeah, there couldn't be a more exciting time to join. I keep saying that, but then it becomes more exciting times. Anyway, there's loads of stuff going on with all of this. And so yeah, thank you for listening. And do get in touch if you want to talk about anything that I've presented here. Thank you.